So I have been told I have to speak English today. So welcome to our very new building, a new meeting room at Alantorum. Today we celebrate two things. First one is the European Day of Statistics. You know that we have I think it's every 4 years we have this World Day on Statistics, and we have every year we have the European Day of Statistics. It's an occasion to celebrate the importance of official statistics as a tool to help decision makers, to help citizens, to help organized civil society to take informed decisions with data where you can rely on. And so I think it is a very important day, especially thinking on all those, not in Europe, fortunately, but in other parts of the world, where statistics is not independent, and it is mere propaganda tool of governments and despots. So it's very important to rely on a state of law and of the rule of law. And we are happy to have this in Europe. So we should be aware of it and we should care for it. So today will take place on, I think it's Saturday, on Sunday, but we thought it's better to anticipate this day because on the weekend we have many other things to do. So the first event is celebrating the European Statistics Day. And the second one is the famous European competition on statistics, which was a very huge success and which is addressed to youth of 14 to 18. And a lot of schools participated, a lot of pupils we saw during the last years. It was a very nice event. And so I think the theme of this year is the digitalization and statistics. And this fits very well with this kickoff meeting, where we have a presentation by Professor Christophe Ley on a stroll along artificial intelligence. I don't know what he will talk to us, but I know it's always of high quality, very stimulating. By the way, he is the chairman of the Luxembourg Statistics Society, so trying to propagate, to make statistics better known by the general public. So with this, no further ado, I will ask Christophe to make his presentation. Thank you very much.
So thank you very much, Seth, for the kind introduction and for the invitation to give this presentation here. This is my utmost pleasure to be here on the occasion of this European statistics competition. And indeed, I was thinking when I received the invitation to give the talk, what would fit well with the theme of digitalization? And so, well, we're talking so much about AI that I thought, okay, let's go with AI. And little could I know that the topic of AI would be so of current interest, because I could not foresee that 2 Nobel Prizes would be given out to people working in AI. So you may have heard last week that the Nobel Prize in Physics was given to John Hopfield and to Jeffrey Hinton. And this is because they developed artificial neural networks, which is a very famous form of artificial intelligence. And for this, they used ideas coming not just from biology, neural networks, but...
Sounds in WebEx. I'm trying to...
Okay. Is it better now? Is it better now?
I think it should be.
Okay.
Yeah, it's good.
Yep.
Okay. Okay, good. Then, so I was just saying that the Nobel Prize in Physics has been given to artificial neural networks, which are based on how our body is supposed to work, and also based on physical principles. And that's why they were awarded this prize. And Geoffrey Hinton is one of the fathers of AI. And actually, his image will also come back on the next slides, but that was prior to knowing that he would get the Nobel Prize. So this is a really nice coincidence. And then on last Wednesday, the Nobel Prize in Chemistry was also given to people working in AI. This has to do with the protein structure prediction problem, also predicting how proteins should fold, should behave in our body for us to be in good health. And what you can see there are three people. David Baker, he has not worked with AI, but he has shown how you can design proteins. But then the combination of Demis Hassabis and John Jumper, they have been the founders of Google DeepMind, and they have built AlphaFold, which is a famous AI tool that allows making these predictions. So this is AI this week has been very famous in with the Nobel Prizes, and that's why I think it's even more of interest to discuss what AI actually is and what is its links also with statistics. But before that, I'm just saying briefly that AI also is present in our society everywhere. I think we all know it, be it for facial recognitions or be it for companies such as Amazon, Meta, Netflix, and so on, who are using AI to analyze our customer behavior and to improve, of course, their own brands. More on this in a bit. So my plan for today is the following. At first, I will actually do a historical excursion about the history of AI, and then we will make really an overview with definitions and links with other fields that you know better, especially statistics, to really put it in the right context. So historically, and I just don't know why I have this on the bottom. It shouldn't be there. I think it wasn't there before. Let me just try again. Yes, good. That's better. So what is AI? This is the definition that I've found on Britannica.com. It's the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. Quite expectable definition of AI. What is probably less expectable is that the origins of AI go back to Alan Turing. So in the 1940s already. We always see now AI is the big thing of the moment, but the idea is not that new at all. It's actually very old, and it goes back to his book Computing, Machinery and Intelligence. You might have seen the movie about his life called The Imitation Game, where in the movie the imitation game itself was not really explained, but what it actually is he designed a game of answers and questions where the goal is to be able to say if the person you are talking to is a human being or a chatbot. So basically, he was already designing in the end of the 1940s a way of how you can see whether you talk to a human or to ChatGPT, which he, of course, could not know at the time. The word AI was proposed by him, but this came up in 1956 at a Dartmouth summer research project on AI. And you see here the participants of that project. They came up with the name. They said, okay, we should call this idea that we have, we should call it AI. And then in the very early AI days, well, that's what people did, that they had to assemble cables in order to make computers work. Those were the very early computers. That's what it looked like in 57. That's why I put this image. And now something that I was very, very surprised when I learned about it. 66. That was the very first chatbot. It was called Elisa and was developed by Joseph Weizenbaum. And it was built on very simple scripted rules. And there was nothing like training it. But you can see here, it was really answering. So is something troubling you? Men are all alike. What is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? So you can see it was trained to engage in a conversation in a much more basic way than we have it nowadays. Yet I think it was I was really surprised to see that this already existed back in 1966, because that shows that the ideas have been floating in the minds for a long time. But of course, the big difference is that nowadays we have the appropriate computing power to do all the developments that have been taking place. Then I'll make a fast forward to 1986, and this is Geoffrey Hinton, who won the Nobel Prize in physics this year. In 86, he has come up with the idea of backpropagation, and that is the basis of the neural networks, of artificial neural networks. And he was basing this on ideas that he borrowed from physics, where you bring information into a system and then you go back and check. While you're going back to your input, you are checking about all the mistakes that have been done, and so you can backpropagate information. You don't just have a push forward, so to speak, but you also can backpropagate, and that way you can refine the error. So his idea there was already based also on the so-called loss functions that we are using in statistics. It was a combination of ideas from physics and statistics, and of course biology for neural networks. A huge upset then about AI took place in '97, when for the first time Deep Blue, a chess computer, has beaten the then best player of chess in the world, Garry Kasparov. And there you can see, also see how it looked like. That was their big watch to check the time, and he was the person playing with Deep Blue who was entering all the commands, and Deep Blue was making the calculations. Up till then, it was never clear that a computer could be the human being. So next, what happened next at the level of AI? So I went for this example: the first autonomous vacuum cleaner, the iRobot Roomba, 2002, that was able to recognize on the floor, could recognize, oh, there is a place where I should go. There is an obstacle, I should not go there. So their image recognition was brought to a new level around the early 2000s. 2010, I had to add this here because that was the moment when DeepMind was created. DeepMind, who has built the AlphaFold, and you can see here, Hassabis is one of the people who received the Nobel Prize in Chemistry. So it is really in 2010 that this incredibly strong company has seen the light, and it is called the Apollo project of AI. It has really driven forward a lot the development of artificial intelligence. I'm of course not giving all the different steps, but in 2014, so 10 years ago, Amazon Alexa came to the world. It might seem longer, perhaps that one hears about it, but it's now exactly 10 years that we have Alexa to whom you can speak and that can recognize your voice. There is an example that I think is probably less well known than Alexa. In 2015, a neural algorithm of artistic style has been proposed. And the idea here is that a neural network, again the neural networks, learns how certain artists draw. And then it's able to repaint a given photo or whatever you want, whatever you tell him, to recreate it in the style of this artist. So here you see the original picture. It's about some town close to a river, and here it is painted in the style of Van Gogh, La Nuit Étoilée de Van Gogh. There you see the original. This is the picture repainted in that style. Here you see Der Schrei from Edvard Munch. It's repainted in that style. And finally, Fire at Sea by Turner. It's done in the Turner style. So the idea here really is that the AI learns to draw in the style of this artist. And how is this done? I'm just saying this because it's again related to statistics, again related to loss functions, except that this time you do not just have one neural network that does this back and forth, but you actually have two. One that learns to draw, and another one that is like the critical referee of how it draws. So basically you have another neural network that is always evaluating how well the first one is drawing, and so besides its own loss function, there is like this second layer of improvement where it's being criticized until it reaches a sufficient level. 2016, the developments become better and better. Now you see here, we make jumps by 1 year, more or less, because there's so much going on in recent years. This is the game of Go, much more complicated than chess because it has so many more possibilities. And it was always believed, okay, chess is now solved. The best chess players can no more beat the best AIs. Okay, we know it, but it will never happen for Go. And then it was even a bigger upset when AlphaGo has been beating Lee Sedol. AlphaGo also from Google DeepMind. So it really has taken over also such a game. And later on, they built even a better algorithm, which is able to learn any game. So this one was, AlphaGo was done for Go, but they made a version of it that is valid in general. It's just, all that it knows is you have to learn a game. It has no tactics whatsoever, and it works for any game. It just has to pick up the rules, and then it's playing an infinite amount, because that's how this works. It plays an infinite amount of games against itself, the AI. So it's not learning. It doesn't start from any theory that we have established. No, it just knows these are the rules, and you should win. And it's bad if you, in the case of Go, it's you have to gain as much territory as possible with your colors. And if you lose a piece, then that's very bad because it's territory for the other. That's all it knows. So it just knows again how the rules are, and it starts with very, very naive ways of playing. I'll come back to a more concrete example later. And by playing an incredibly large amount of games against itself, it just gains so much experience and knowledge that it becomes better and develops better strategies than humans could ever do. It's like in 1 day it has played more Go than the Go champion has played his entire life. On the medical level, this was in January 2017. That was for the first time that deep neural networks have been used to recognize whether or not melanoma that you have on your skin are benign or malign. And it has been able at that point to reach the same level of accuracy than doctors. Of course, since then, it has been more and more approved. And nowadays, this has really become a very useful tool for the diagnosis for doctors. I really underline it. It's a tool, because it's not the AI that's making the decision, it's the doctor, but they are more and more using it also as a help. This is a funny one, 2018. So I told you about, we have just seen about how you can recreate the style of artists. Of course, when you think this a bit further, you can also recreate what people look like, basically. So what do we have here? This is the source. So here the AI learns, okay, that's a person, and I'm trying to learn what is special about him, and I try to draw in the style of what this person looks like. And here is then my input. And so what you see here with the picture of this lady is now turned. This is what a combination of them would look like. This is a combination of them look like, combination with the child, and so on. So all these pictures that you see there are totally recreated. These are people that do not exist, but that's what they would look like if they were merged, so to speak. And this is, of course, I mean, this generator is something very powerful. It also obviously also has dangers because, well, you're creating tons of pictures of people, and you can no more say, is this now a real person or not? I mean, we have seen that on the news. I think famous images of Trump, Obama, Merkel, where they were doing actions that they never did in reality. And now this goes in a sense even a step further, where you just create new faces that are not existing yet on Earth, and probably never will exist like that. 2018. That's the reason for the Nobel Prize in Chemistry. Every year there is a protein Olympiad, that's how they call it. It's called the CASP, Critical Assessment of Structure Prediction. So basically, researchers come together and they try out their best ways to predict protein structures on on proteins that they haven't seen before. And AlphaFold in 2018, they were just completely crushing the competition. So their best competitors got something like 8 out of 48 proteins correct, while AlphaFold was about 25. So that was something totally unseen, and by now they have become even much better. They are reaching near perfection, while before really you could not get more than 10% correct, perhaps, or a bit more, 20% correct. So this was a huge step forward, and it's even called a game changer. 2022, ChatGPT, yes. We know. So I asked ChatGPT. I asked it this weekend. What is static? And that's the answer that it gave. It was actually a very long answer. So it had a lot to tell about what static is. What are the missions of static? And we know ChatGPT is a large language model, where the idea is that at any moment it has learned from all the text available on the internet. It has learned what is the probability if I'm writing this word that then next has to come another word, and so on and so on. So it's all based on probabilities and statistics. It just knows this is the most likely way to continue a sentence and to answer to this question. It's really all based on statistics and probabilities that it has learned through a huge amount of training. And ChatGPT is the most well-known because it was the first that came out and was available to the large public. But of course, you have many other large language models. There are also now large language models for official statistics that have been developed or are currently more under development. So this has also been a big change. We call this generative artificial intelligence because you ask it a question and it generates something new. So here it generates text. That's why we call this generative AI. So that was my little historical excursion. And now let's come to the overview that I had mentioned before. And I think this overview is to me a very important one, because it really gives an idea of how you can perceive AI. So AI is everything that is in this very big circle. And let's stay a bit outside of everything that concerns learning. So here you have what you call rule-based artificial intelligence, when you know if this happens, then that happens, or scripts where different rules are set one after the other. Robotics, for a big part, belong to this outside category. Then to AI belongs the field of learning, and everything that comes below here is part of learning. So learning is the biggest part of AI. And here, when I'm looking outside machine learning for a moment, this is everything that has to do with learning from data. And here, statistical methods that we know for a long time are part of it. Linear regression, logistic regression. You learn from data. These are statistical approaches. But that is where you have the intersection with statistics. It's in this part of learning, because it's everything where you can learn from data, which is done in a linear way. And then machine learning, this is nonlinear modeling. So this is where the machine learns, in a sense, more by itself to find links, because when we are no more in the linear modeling world, we are not telling the machine, please find there should be a linear or polynomial relationship. We are no more telling that. Where like in linear regression, we say, or the goal is to estimate the parameters such that our input and our output match in the best possible way. Here we use different types of algorithms, such as random forest or support vector machines, to cite about these two, where we do not say there is a linear relationship, but we tell the algorithm, please learn the link between input and output. And this can be a completely non-linear link. And that's a big part. Most of the time, when people talk about AI nowadays, it's actually machine learning. That's the main part. I think for many people, it's not clear that statistics has also this strong intersection with AI. But it's something I like to tell in my classes. Yeah, you see, what is linear regression? is this for you? Because it fulfills all the categories of an artificial intelligence. But it has been out there way before anyone was talking about AI. So there is a very clear and a very strong intersection. And within machine learning, you have the field of deep learning. That is everything that concerns neural networks. And then here, the smallest circle, this is generative AI. This is ChatGPT and company. I wrote here transformers because that is a technology that has been invented in 2018. The transformers are the basis of our large language models, of everything that concerns ChatGPT, of everything that concerns DALL-E, or nowadays you can also create, when you write some input, you can also create videos. It can create videos for you. All this is called generative AI, and it is based on transformers. And it's also important to see that this is really just a small part of AI. Because that's something that I find a bit suboptimal, is that since the advent of ChatGPT, many people, they do associate, oh, AI is ChatGPT, or AI is then generative AI. But it's just really a small part of it, an important part of it, but a small part of it. So here I have, I just give a small definition of what the term machine learning actually refers to. I think it's very obvious for everyone here. In our traditional programming, you have data and you have a program, you get the output. You can do this with calculations. When I say 8 and my program is take to the power 2, well, I'm getting 64. Well, we all know how this works. It's on our machines. In machine learning, it's different. You give it as entry point the data and the result, and it is supposed to find the program that links the two. So 8 and 64, 7 and 49, it would supposed to find that, oh, the operation that we want to do is taking the square. That's how the machine learns, when you give it the input and the output. So it's really like reverse engineering from what we typically know how programming works. Now, let's go on a bit more concrete example. And for this, I'm taking football. Let's suppose that Belgium plays against Luxembourg. I could have taken Bulgaria, as this is of more actuality, but let's go with Belgium, our neighbor country. So at first, when you want to define such an AI, you have to define a goal. What do you want to achieve? So in this case, we would like to predict the number of goals that each team is going to score. Now, what do we need for that? We need to find the so-called determining factors. Which factors can be of importance to reach our goal? Well, in this case, you can think, okay, what do we need? What is important? Well, for instance, the average age of players, previous results of the different countries, the level at which the players are playing, because that is very, very important to see that Belgium might be perhaps just a little bit stronger than Luxembourg. And once we have these determining factors, we of course need to collect data. And well, for that, we just collect previous match results of the two teams. And then finally, you train the AI, which means that the algorithm has to learn based on all the previous matches and all the data that you have. It has to learn, okay, if two teams face each other, then these determining factors play an important role. These determining factors play a less important role. And in the end, it will come up. Every determining factor will have a certain weight and will act on the result in a certain way. And when then a new game happens, like this game, it will say, okay, these are the factors, that's how they come into the play, and boom, I'm predicting that Luxembourg will win 4-1. That would be what probably unlikely AI would say, but this is how machine learning works. And again, if we think about it, all that we put in here is what you do also with linear regression and logistic regression. It's exactly the same. The only thing that is different is that here you have different algorithms that actually can learn this linear. You're not imposing the fact that it has to be linear, but for the rest, it's exactly how linear regression also works. So what we've seen here is what you call supervised machine learning, because you have a set of predictors, x1 to xp, and you have an associated response yi, and it learns the link between the two. That's the only mathematical part that we have there. And what is also different from what we use in statistics is that in machine learning, we say that you learn from training data because you train your model. While in statistics, we talk about you have data and you estimate the parameters of your linear regression. And of course, just as linear and logistic regression, the response of in supervised machine learning can be either quantitative, that's what we just had before with the goals, or qualitative when you make a classification. And so in a classification problem, it works all in the same way. So suppose that we want to predict whether or not a person is going to suffer from diabetes. Again, you need to find determining factors, age, body mass index, and so on. Collect data, people that have and do not have diabetes, very important. And then in the end, again, the AI is trained in exactly the same way. Now for a more complicated example, image processing. And it's really here where we go into this second last bubble of deep learning. Because this requires a lot of information to process images. It works still in the same way, so you will see that I kept the same pattern. Our goal is to classify images. For instance, is this a cat or not? To take a very simple example. We'll see some more important example right afterwards. So you need to find the determining factors. How could an AI learn about an image? And actually, all the AI needs are the pixels. It really I'm not finding this word in English. It's from the medical word sezieren. It looks in very detail. It takes completely in detail a picture. So for instance, here it would take picture by picture. It would analyze this image, and then see, okay, how dark, how bright are the pixels here? What colors do they have, and so on and so on. That's how it learns. It just learns based on how the pixels are put together. To reach your goal, you need to have many images, in this case with cats and without cats. And again, you have to train the AI. In this case, the best AIs for this are really neural networks, because in neural networks, you can process a very large amount of information, more than with other algorithms such as random forest, for instance. For images, neural networks are kind of unbeatable because there were also specific forms of neural networks that were made for image processing. And that's what I said. This is part of deep learning. I'm giving you here two examples. Well, that's the first example. Recognizing cars. This is for the advantage of self-driving cars. So you see, this is what can be recognized. And so the camera can see, okay, there are cars. This is street. There's something else. So again, you really see here the importance of the colors and of the pixels, how it works. Going back to medicine, this is also used a lot for diagnosis. So here you see one example where it is supposed to find if there is something odd going on in a person's body, and so it is able to detect there is something that is not so good. There are parts that are healthy, but there is something that is not good for the patient, and so it helps in the diagnosis. Image recognition is being used more and more. There are more and more developments, also in orthopedics nowadays, to recognize whether or not there is a fracture. So I'm just putting you so all this still is part of supervised ML, also images, because you tell the computer, you tell the AI, this is an image with a disease, this is an image without a disease. So it's still, you are the one who tells him, learn from this. This is your input, this is your output. And so here I'm giving you various such popular supervised ML algorithms. Of course, we start with the statistical ones. Then here, lasso and ridge regression, which are definitely also part of statistics, but they are like a bit closer to the ML world, the pure ML world. Let's call it like this. Decision trees, which are also, they were born in statistics, random forest, boosting algorithms, support vector machines, and the neural networks. Now, moving to unsupervised machine learning. That's also an important part. So here, we just give the determining factors to the AI. We are not telling the AI, this is the output that you should learn. No, we just give it the data and we ask it, make something out of it. Find a link between the data. Give us some information. And a famous goal of such an AI can be clustering. So I give you data, find a link, put together observations that are for some reason similar. And so for instance, here we see the Simpsons, famous cartoon, and you could ask, how could you cluster them? Well, there is not only one answer when you cluster objects. Here on the right hand side, it's in males and females. On the left hand side, it's clustering according to these are members of the Simpson family, and these are employees at the school in Springfield where the Simpsons are living. And yeah, there are plenty of concrete examples of this in our real lives. And now I'm coming back to the slide from the very beginning when I was talking about our consumer behavior. These are clustering techniques. When you watch Disney Channel on Amazon or on Netflix, whatever, when you watch different movies, you know that they are suggesting you based on what you've watched. We suggest you might like this, or on Amazon, based on what you've purchased, we suggest you might like this. But what they do is they have your profile and they make this clustering. So you are in a bag of people, and they know what the other people in that cluster, in that group, like to watch or to buy. And then you receive this as a suggestion next. And the more information, the more we use this, the more information we give about ourselves, about our choices, and of course, the more concrete, the more accurate these predictions then become. So this is unsupervised machine learning. Difference between supervised and unsupervised. I give you one short example. Recognize what fruits it is. So here in supervised, we would say, these are examples of apples, grapes, cherry, and banana. Now learn, this is a banana, this is a cherry. Unsupervised, we would just tell him, these are fruits, find groups. And well, if the AI is doing it very well, then it would recognize, oh, there are different shapes and different colors. So it just says all these, I'm putting all apples together, all grapes together, all cherries, all bananas together. Might also be that the AI is not able to make all these distinctions and perhaps say, oh, I try to find clusters, so I'm going by colors. And then it would put the apples and the cherries in the same group if it goes by colors. So you see, that's really the main difference between the two. Next group is reinforcement learning. And that is the basis of Go, chess, of all these games, but also of AlphaFold. So the idea here is that you learn by failing. You just give the overall rules to the AI, and then the AI has a so-called agent. An agent is supposed to find its way through a jungle of obstacles, and we tell it what is not good, so what is bad, what is a failure, and then it tries to learn from this and become better and better and better every time that it actually does the same action all over again. So the goal is to maximize the reward. And let me give you an illustration of this based on this very old game, Super Mario Brothers from Nintendo. So Mario's goal is it starts here on one place and it has to go to the end of the level. Okay, so how would this work? In the very first run of an AI, the Mario would just be standing there, doing nothing, because it doesn't know. It just knows, okay, it can move, it can jump, but it doesn't know that it's important to do this. So Mario will stand there, and most likely Mario will just die because the timer runs out. So the AI will then learn, okay, just standing is not good. Let's do something else. And then it might discover, okay, I can walk. But then you have the first enemy, a Goomba typically, coming up. Mario just runs into it, boom, dead again. So it knows, there's something that's also not good. And so it might be that next time there's the Goomba, and he learns, oh, and he jumps over it. And then he will have survived this. But then he will run, there is an obstacle, a wall over which you are supposed to jump, but he will just walk into it and continue to walk into it because, again, he doesn't know that this is bad. And so while walking into it, the timer will again run off. And the next time it will jump over the Goomba, jump over the wall, and so on. after 35 trials, it does the level in a perfect record time. It has learned all of this, and it does it better than most expert human players. So that is the idea of reinforcement learning. And this is also the idea, as I said, behind chess. You learn from your mistakes, and also for many other tasks, such as the classification of proteins. It learns by itself, by making mistakes, and this is what you call reinforcement learning, because here you are not saying learn this relationship. No, you just say there's a goal that you have to achieve, and this is what could go wrong. And then it learns by making mistakes. And I'm putting this there because this reinforcement learning, try, fail until you have success, is exactly, so neural networks are like our human brain works, but this reinforcement learning is just like children learn. Children learn by making mistakes, by falling down. That's really very close to what reinforcement learning is. And then finally, well, generative AI, ChatGPT, where now you learn from a lot of input data, and it's statistics, probabilities that tell you what is the most likely element that you should generate. Large language models, they can produce text. ChatGPT produces text because it has learned, it has received a lot of input, and it learns to the link between different words. It knows what is the most likely next word after this first word. Images, this is DALL-E. For instance, DALL-E is a way how you can you input text and you receive an image. The same happens. You can make text to speech, text to music. You can also now create music. Code can be created for you, or video sequences. And of course, I have to end by some concerns. I'm not going through all of these, but these are typically concerns. I was speaking about the creation of music. So artists, they are not very happy about this, because people can use an AI to create music. Cheating, hacking becomes much easier. Fake news become much more easier. How does education have to adapt when ChatGPT is around the corner? It's not obvious. Will jobs get lost or not? So there are various threats, and this is why many people are afraid of AI. And this is why I think it's so important. As Serge had mentioned, I think it's important in general that people get a better education in statistics to know a bit more about numbers, because that will also pave the way to a better basic understanding of what AI is. And when you have that, then you can better perceive, okay, what are real risks, what are perhaps just imaginary risks. How can we deal with this? Because the revolution has started, the AI revolution. I mean, in 1940s already, but still, nowadays it's there. It has changed a lot, many things, and so these are important aspects that need to be considered. Ethical aspects, very important. And I also want to stress this, that of course AI is using a lot of energy resources. Training ChatGPT has cost an enormous amount. And this is also something that we should reflect about, especially also when it comes to data storage. So much has been created, and this is a question where that's one of my concerns, the huge use of energy resources. One way to get a better control on all this is responsible artificial intelligence. Well, that's the last type of AI that I have to mention, that I will mention. The OECD has put up this goal. It wants AI to be innovative and trustworthy, and that it respects human rights and democratic values. And so the following aspects, they have to be ensured in the future for AI. It must be fair and robust, which means reliable, and we must know, okay, it always produces similar results. Data privacy, I think that's a very big aspect that you all know excellently well about it. That must also be assured. Human control, as much as possible. We should not give it out of our hands, so to speak. And in order for all this to be possible, AI must be explainable. All too often, it's a black box. And then things like this can happen. This is a funny example, but still. So I told before, learning whether it's a cat or not. Here, the goal was dog versus wolf. And in all these images here on the left-hand side, you can see it correctly said it's a wolf. And on the right-hand side, it correctly said dog, dog, dog. But here it said wolf. And why so? Well, sorry?
There is a lot of snow.
There is a lot of snow, exactly. It's just because the AI has learned on all its training images, oh, snow, that means wolf. And so it has learned that actually, whenever there's snow somewhere, it must be a wolf, which of course is not correct. So, and here it is because people have developed something that is called interpretable machine learning or explainable AI, that it was possible to look what is the reason for this wrong prediction, then understand it. And that is what we need. We need to have this explainable AI. We must be able to control how the AI reaches its conclusions, reaches its result, because then, only then, we can really face the challenges that lie ahead and get some more, get the required control over this otherwise really excellent technology that has a lot of advantages, but to this we need to have this required basic understanding. So I hope that I could give you a little bit of an overview, a stroll along what artificial intelligence is, and I thank you very much for your attention.
Agree to take some questions?
Sure. Sure.
Thanks a lot for this great overview and listening to you. So we have artificial intelligence, we have statistics, and my question would be, in the end, what is the difference between now all of these artificial intelligence techniques and statistics or traditional statistics? Or is this just yet another kind of statistical technique which has been somehow proposed, and there are reasons why all of this is happening? You've mentioned them. So we have more computing power, we have access to larger data sets, and then we can come up with all kinds of amazing new use cases. But in the end, is it just yet another form of statistics, or is it something else? So, and one thing is, well, you mentioned, for example, here explainability. Well, we are still very much black box type of approaches. I mean, generally speaking, all of this compared to traditional statistics, it lacks a bit of a theory sometimes. Maybe I'm wrong, but yes, so I wanted to learn what is your point of view? Is this just another form of statistics, or is it something else?
Those are very good questions. I'll first come to the second part of what you said, because that just now sticks in my mind. Yes, we are indeed lacking a certain theory on various aspects, and this is something that really needs to be studied. We need to, for instance, statistical learning is a field within statistics where the goal is to study machine learning models with from a mathematical, more theoretical point of view. So this is a field that is out there, but it needs to go much not faster. It needs to go much deeper, because we still are lacking the required theory. A lot has been done, but for instance, only recently have we also here in our department started to study from a mathematical viewpoint neural network. So this is still lacking. It's in process, but it needs to be more, especially since there are so many new technologies that are really being brought out. It's not possible to keep up with this pace. The theory cannot always keep up with the pace of everything that is brought out on the market, because you have and this is also already partially answering your first question. In AI, you have a lot of people from computer science that also produce new software, new algorithms, which are very, very good, and where the goal really is at every time to improve the prediction, to get better and better predictions. But this is really purely prediction oriented. It's not studied. It's not proposed from the point of view where we would say, oh, we have these loss functions, or where we have we want to achieve a certain generalizability. It's really from the pure goal of prediction based on training and test sets. So that comes from there. And then of course you also have industry. There's so much coming also from the industry, and they also they do it in the same way. They also don't study it from the perspective that we would be accustomed to, having the theory behind it. They are producing incredible algorithms, such as AlphaFold. But this is what I think is making one difference. There is way more computational power, as you said, but also many more people from other fields that work on it. Now, as for another difference, yes, I mean data science. Data science to me, and I know we had this discussion more than once. Data science to me is a rebranding of very modern statistics, where you bring more from other fields into it. But in essence, to me, I always say it's statistics 2.0, data science, which already is different from the basic statistics that we know it. And AI is, in that sense, I would say some of these algorithms, since they have not yet been studied from a real statistical perspective, that's the big difference. You can propose something without that you know all the uncertainty, for instance. That's I would say a very clear difference. But you also have people who say, well, a neural network is a very big combination of linear regression models, because when you go from one layer to the other, that's what you do. You again go back to the essence of statistics. And a funny thing when we talk about, because you also mentioned explainability, is that one way to make AI explainable is this is a method called LIME. I don't have it in my mind. Linear interpretation, and then I'm lost. But the goal there is to, for instance, take a linear regression model, take your complex AI model, and try to find locally the linear regression model that is the closest to give this answer, and then be able to get the explanation from your linear regression model. So, and you have to do this for every output instance. And so yeah, the links, they are so strong. Yes, they are very much there. But yeah, uncertainty quantification, bigger computing power, those are the main differences.
Okay, so I just want to make a little bit of a reflection speaking about AI. So, well, recently all the people are speaking about AI like something bad is going to happen, you know. So we are afraid what is going to happen. So I just want to remind that even where the internet was coming in, our website was coming in, we were all afraid about what's going to happen. But in terms of productivity or labor market, I'm just looking from that point of view. Well, it saved a lot of lives. It augmented other types of jobs. It augmented the productivity. So, well, it's not that bad. So, example, just 2 days ago, I was just writing a code and I'd made a mistake, and it took me like, before, it would take me like 3 hours to find the error. But with AI, it took like 5 seconds, and it was the perfect. So it's fine. So just to see from another point of view, so every revolution has its black period, but then it's a bright period coming in. So it's not always bad. So, okay, we need more time, but AI is doing a lot of work that we should recognize that is doing good, not only bad. So I just want a little bit of this reflection of
that's very
always
clear.
Speaking bad about AI. So
that's clear. And I hope I didn't sound negative.
No, sorry, but I entered a little bit late. So, but recently I heard a lot of people being afraid. Yeah. Even the Nobel Prize, who actually invented the AI, he spoke a little bit. Be careful. Okay, so we should be careful. But let's go back a little bit in this history and everything. So I just want to ask you another question. Is that when I do a little bit of lasso regression, not more, when I see the difference when I do a linear regression or a simple multivariate regression and I do a lasso regression, well, sometimes the difference is so small, or it's sometimes lasso regression always says to me that OLS is better. So I want to ask you, so given not only your statistical experience, but also data science experience, so when it's worthy to use this more complex model, so when we have big data or when linear regression is not predicting so well, so I'm just confused a little bit. Is there a rule of thumb, or is there a theory behind, or something like that?
Oh, yep. That's also a very deep question. So there is no theory behind it as to which one to use when. The way I like to say it, and for this talk I did not go into that detail, but the way I like to say it is the following: statistics is a top-down approach, where you say this is the model I believe the data the data will follow, and you're estimating the parameters of your model. Machine learning is bottom up, where you say I have an algorithm, these are my data, and the data tell me what is the relationship. You lose here the interpretability that you had with statistics, but you gain in generality. So you have these two approaches. Which one to use when? Well, I had that's what we had in this course that we had once together. You can actually see in certain instances when classical OLS is doing better, or when lasso is doing better. The lasso really comes in when you have a lot of input variables, but really only some. You might have the feeling that perhaps many are not necessary, and you want to get away with them. Then you can really see from what point on, when you have, like, let's say 50 variables and only 10% of them are of actual value, then you will gain by using lasso. So when you have this suspicion that I have a lot of input, but I don't know if this is really useful, then I would say lasso is definitely better. And now, as to other machine learning models, this I would recommend to use them when you have no clear opinion as to why you should use this model, this statistical model. Then I would say go with a machine learning model. And yes, when you have big data, this becomes more and more the case, because there you have, it's more difficult to really find the right model that you should use. So what we are using in my research team is we typically use, when it's possible, use a lot of different models, and actually also including linear or logistic regression, to in the end see, okay, which one fulfills better the aim. And if there is just a tiny gap, I will go with the statistical models. If there is a big gap, then I would say, okay, I'm using the other models. And for the rest, I totally agree with you. There are plenty of opportunities, and that's why I said, if we can fulfill like this, then we should really embrace this as a great opportunity. It's important to know about the challenges, but especially it's important to somehow demystify it, because that is what is creating the biggest fear in most people. And again, if people knew a bit more the basic statistics, they would also be better prepared for this.
Yeah. I have a question online asking if you could quickly re-explain the main difference between supervised and unsupervised learning.
Okay, I can use again these slides. So supervised learning is when you tell the machine, listen, this is the input, that is the output. Please find a link between these two, such as on these images, this is an apple. I give you tons of images of an apple. This is a banana. I give you tons of images of a banana. Please learn now to recognize it. Unsupervised learning is when you say, I'm just giving you data. I'm not telling you what to do with it. I'm just telling you, put them, for this clustering, put them together, put those together that resemble each other. But I am not telling you that this is an apple, this is a banana. No, you should find out by yourself and group them in a way that you deem makes groups that look the same.
Yeah. I have another question about the machine learning. So it classifies the variables based on some knowledge, right?
No, just based on the data that you give it.
Okay, so he sees the data, but when you do the example of Simpson, so he says that there is the Simpson family, and there is so he knows something about that, right?
Yes.
So he has some knowledge before.
You go to a very, very good point there. This is actually an excellent remark. This example, I like to take it to show that clustering can be different, but an AI would not cluster like this.
Yeah. Okay.
An AI would not do it like this, because it would require indeed this knowledge about who they are. Very good point. Yeah. And about unsupervised machine learning, I can tell you another example of it, which again shows the link with statistics. Principal component analysis is a dimension reduction technique that we know from statistics, and it is part of unsupervised learning. So there we have again a statistical technique that is part of AI. And actually, it's the two most famous techniques, clustering and dimension reduction, that are associated with unsupervised learning. Yes?
I wonder for a statistical disclosure control, whether we have a new friend or an enemy here. Do you have a reflection on this?
Whether AI is a new friend or an enemy? Well, I would say in a sense it's a competitor, but like with but it's a competitor that is also a big help, because you can learn from it. It also gives to statistics new tools and a new attention also on it. And so I would say it's like it's like also the same way that you have in sports. When you have two rivals, they bring the best out of each other. So I would see it like this. It can be perceived as a rival, but that should bring the best also out of statistics and give it a new boost, just as what happened with data science.
I have the impression that the existing statistical confidentiality procedures will be completely blown away by this, but there might be possibilities to do something to create sufficient uncertainty, but this will create a communication problem with the public, that your data has an additional form of uncertainty to protect our respondents.
Oh, yeah, I mean, I think the uncertainty communication has always been an issue, and one of the difficulties that we as statisticians face when you have to say this is what we project. Static does a lot of projections. What we project for the next time, and you never have a certainty, of course, about this. This has always been difficult, I would say. Well, for instance, the last thing I said with this explainability, their statistical techniques, they come into the game for AI. And speaking especially about uncertainty quantification, there is on the one hand side currently a link that is being created, because it is being recognized that these elements from statistics, they are needed in AI, because AI can do point prediction. That's actually also something that is true for the AlphaFold. They can make point predictions, but they are lacking the uncertainty, and that's something that people in biology are looking for. They are asking for that. So there is this request to bring statistical elements in there. And then there is also something that is called conformal learning, which is really a statistical version of AI. So now it's really a time where elements of statistics are being brought in, because people have started to recognize that we need to quantify the uncertainty. So I believe that this link is becoming stronger and should be beneficial in the end for all parties.
Okay. So should we close our session, our kickoff meeting? You made a very interesting historical perspective and explaining how all the different techniques fit together. You made a training at Statec, when was it, last year?
January.
In January, so I thought it was last year, but January, which is where a lot of people coming, because I think everybody's interested how it works, how can we learn it, how interesting is it? By the way, my Linda, she only gives the positive aspects, but after your training, I asked her to rerun our rest of a very nice paper with a lot of variables where we could have a nice narrative. And she rerun it on Lasso. And from all those nice variables, it had only 3 coming out.
Okay.
and we had problems to interpret. So just to say, it's not always so easy. So, but it's very interesting and very stimulating. And I hope that we will have the opportunity to make new trainings here, especially for our colleagues, because those are techniques that we have to learn, and it will be. I suppose in the next years we will not call ourselves statisticians. Okay, so very much. It was very interesting, and so I thank you very much for this presentation.